Okay, so let's get started. This will just be a quick video to help with exercise 9D, question 14. I'm not going to do your question, I'm going to do a question that's similar and talk through some of the thinking behind it, some of the rationale in the approach that I'm going to take. So we have two particles, A and B, and they're moving along the same straight horizontal line with constant accelerations. The acceleration for A is 2 and the acceleration for B is 4.2. At the time t equals 0, so at the very beginning, when we first started measuring time, the particle A passes the point X with a speed of 7 meters per second. 2 seconds later, B passes with a speed of 4 meters per second, also moving in the same direction as A. We're asked to find both the time and the distance from X where the particles meet. Alright, so just so you can visualize what's happening, as I look at these values and I collect the variables together, I see that particle A, although it starts first, its acceleration is not as high as the acceleration for the second particle, which means that at some point the second particle is going to catch up and even overtake. Every second, these two particles are getting closer and closer together until the second particle, particle B, overtakes particle A. So looking at the numbers, that's something we should be able to gauge, we should be able to gain from this scenario. So I'm just going to go ahead and I'm going to collect the variables that are in the question. So for particle A, what SUVAT variables do we know? So I don't know what the displacement is, but I do know the initial velocity is 7. We don't know the final velocity, but I know that the acceleration is 2 and I have an unknown time. For particle B, I don't know the displacement. The initial velocity is 4. Final velocity is unknown. Acceleration is 4.2. And the time, now this is the important bit, the time we're going to describe as t minus 2. Now, t equals 0 is an indicator that we're at the beginning of the journey, that we're just about to start. We're not actually in play yet. We haven't gone past the starting line, but we're right there on the starting line. That's what t equals 0 usually indicates to us. So I want you to keep that in mind as we work our way through today's problem. If we go back and we look at the way that these particles are moving against each other, I realize that if I've called the first particle's time t, after 2 seconds, the second particle starts its journey. But since it's the beginning of the journey for the second particle, I need its time descriptor, I need its time expression to equal 0. And the way that I get that is that I have the first particle's time subtract 2. So when the first particle is on 2 seconds, the equivalent for the second particle is 0 seconds. When the first particle is on 3 seconds, the equivalent for the second particle is 1 second. When the blue particle is on 4 seconds, the orange one is on 2, 5 and 3, 6 and 4, etc., etc. Now, as we track these values, I hope you notice that the time for the orange particle is always 2 less than the time for the blue particle. So whatever time it is for the blue one, we can refer to the time for the orange one as time minus 2. The blue one's t, the orange one is t minus 2. So naming the time variable for the second particle to move is really important. It is going to be the time of the original particle minus however long you waited before you launched the second particle. So in this case, t minus 2. Okay, as long as you keep that, we know that t refers to the first particle in motion, whereas t minus 2 is what we use in reference to the second particle in motion. Now that I have all these variables, I'm going to choose a SUVAT equation that combines the ones that we have with s, with the displacement, because I'm trying to find the distance from x. So I'm going to go ahead and substitute these values in, and I get an expression for the displacement of A. You can notice I use a subscript just to be clear which displacement I've calculated, and do exactly the same thing for B. Okay, we're interested in a particular value of t in a particular time where both of them have traveled the same distance from x. Maybe both of them have gone 50 meters. Maybe both of them have gone 100 meters. I want to know what value of t at what time do both of these have the same displacement. So I'm just going to set out an equation for this scenario where the displacement of A equals the displacement of B. I've got an expression for the displacement of A. I've got an expression for the displacement of B. I'm going to equate them together and solve. Okay, I've got some tidying up to do on the right hand side. I can square this algebraic expression, t minus 2, we can square that in our heads, and I can simplify by expanding the brackets. I see here that I'm going to be working with a quadratic equation. I've got t squareds, and I've got t to the power of 1, and I've got constants. So just some careful rearranging, moving all of the terms onto one side of the equal sign, and then I can just go ahead and solve. So you can use any technique that you'd like to solve. I think you're probably best off using the equation solver on your calculator or the quadratic equation, and we get two results. We get t equals 0.0352, so that's very, very quickly after the initial movement, or t equals 10.33. Only one of these makes sense. At the time t equals 0.0352, the second particle isn't even in play. The second particle hasn't even gone past x, so that's not the value we're interested in. Sometimes you might get negative values and you realize that's not the one you're interested in. We're interested in t equals 10.33. The question additionally asked, what is the actual distance? So now we know the time when they are the same distance away, but what is that distance? I can find that by substituting this time into one of those expressions for displacement. I hope you realize that it should actually work in both of them. So I'm actually just going to choose the easiest one to substitute into. So I'm going to go for 7t plus t squared. And I'm just going to substitute in my 10.33. And that gives me an answer of 179.02 meters. So the key thing here is just be really careful how you describe the variable, the SUVAT variable of time for the second particle. It's going to be t minus whatever the time difference is. So if it started 7 seconds afterwards, it will be t minus 7. The way to think through it is that after the first particle has been in motion for 7 seconds, I want the second particle to have the effect of only just starting to move, or have the effect of being at the beginning of its journey. And the beginning of its journey, I think we're familiar now, we usually refer to as t equals 0. So hopefully you can use that to always make sure you get the right expression for time in the second variable.